Hello, hello. So today I'll be covering a bit more on the merge sort we wrote last time. We're going to be doing some applications of it, and then we're going to actually see. Hold on, just fixing my exposure really quick. Yeah, the other way. All right, there we go. So we'll be doing the merge sort that was last time, but this time we'll actually be applying it a little bit more. What we'll be doing is we'll be doing first a generic merge sort where we can sort any kind of object. Right now, of course, we can only sort ints. Then after I do this non-generic merge sort, we'll do the next step, which is to actually apply it in an algorithm. And then we'll see how we can use it to both make what's called a greedy algorithm and to do some alphabetization. So we can, take, let's say, the B-movie script and put it in alphabetical order of all the words, and then maybe what we can do is actually count how many words, like how many of each word were in the movie script. So those could be our little projects to use merge sort. But before we do that, before we sort strings or do a greedy algorithm, what we're going to have to do is we're going to have to actually know how to make merge sort work on any kind of object. And for that, we're going to need interfaces. So let's get into it. I see one of the hands is up, so what's up? Yeah. Yes, I'll be putting it up on GitHub afterwards. Sorry, I didn't put the last one on GitHub just because I didn't have time for it, but I can go back and, yeah, retroactively do those. Yeah, definitely. So, thank you for the pointing it out. Yes, it will be up on GitHub at the end of this, and I'll post it as soon as it's done. Though during the session I'm still writing it, so obviously I can't put it up before it's fully written. But yeah, so today we'll be doing making our merge sort into a generic merge sort where we can sort any kind of object, and then we'll be doing a few applications of sorting, which will help you out later on in technical difficulty. Sorry about that. So I'll give you a quick recap of merge sort first, and then I will get into actually applying it. So merge sort is a divide and conquer sorting algorithm. So we have a divide step, which is here, where we basically split our array in half until it can be split no more, and then we merge our arrays back together in order. So here we had our divide method, and here I have merge, which is kind of our conquer method. And in merge, we'll put together our stuff, and we'll make sure that it's in order as we're merging it. All right, so those are the two steps of merge sort. It's the divide step and the conquer step, as I call them. If you want a lot of detail on this, last session we actually spent the whole time just writing out merge sort and explaining every single step. So the Tuesday session recording is where you'll want to go to see that. Today we're going to assume that we know how to write merge sort, but I'll just quickly go over the algorithm once again, in case some of you know it in theory, but just need a recap. So it's recursive. It divides our array into smaller bits and then puts them back together, and it's very fast. First, it has divide step, where it recursively breaks our array down into smaller subarrays, which can all be sorted individually. And then after that step, it will have a conquer step where it takes the divided subarrays, which are actually all individual, because the base case of our division is when it's an individual unit, and then it puts them all back together into our final array, which is sorted. Right? So it has a base case, which is where all of these arrays are broken down into the smallest bit of size 1, because of course an array of size 1 is always sorted. Then it takes these sorted subarrays and it merges them together. You can see every subarray here is sorted, and it puts all these subarrays right back together up until it gets back the sorted array. That's the general algorithm. Now this is the parts where we actually get really into it. We're going to do an interface, and we're going to use comparable, iterable, iterator. We're going to use all of these in order to make some algorithms which take our merge sort and actually use it. So before we get into this, using the merge sort, we'll have to create something that we can sort. And a problem a lot of us might be facing right now is the problem of internships. There's so many of them. There's hundreds of them out there, right? You got so many companies you're going to apply for. So how are we going to write an algorithm which can let you choose which ones to apply for based on priority? So that's what we'll do today. It's called a greedy algorithm, what we'll be writing. So the first thing we'll write is we'll write the class for internship. So how do we define our internships? We'll say internship is a class, and we'll make it really simple for now. We'll just have a name. So string name, and we'll have a number which represents how much we want it. So we'll have an int, well, maybe actually we'll have two numbers. Let's say we'll have an int pay, which is how much the internship will pay you, and then we'll have an int cool factor. Because obviously we need something that's cool and that's going to pay us a lot of money. We're going to quickly generate a constructor, which is really easy to do. It's just code and then generate constructor, and that's going to give us a constructor for our internship class, which is going to take all of these things in as arguments, and it's going to make one. But now, here's the spicy sauce that's going to let us sort it. What we need to do is we need to say it implements comparable. And we're going to be able to compare it to what? Well, we're going to compare it to other internships. Right? So now, with comparable implemented, it's going to ask us to implement the methods. What comparable does is it allows us to compare two objects together. So here, it's going to compare to internship O. We can see here, in the triangle brackets, this is a generic. If you remember generics, I think it was from tutorial 5, generics are a way to tell the compiler that there will be a class there, but not tell it what class that's going to be. So when we say it implements comparable of internship, it means an internship can be compared to another object of type internship. So when you compare to, it'll take as input whatever you have here. If it's comparable to, let's say, a string, which would make no sense, because why would you compare internships and strings? But if you do that, what we'll need to do is we'll need to implement compare to, and now it's going to actually compare it to a string. So whatever you put in here is what it's going to be compared to. Since we want to compare internships to other internships, we'll put it like this. And I'm telling you, it's almost always the case that you're going to be comparing objects of the same type. It's very rare that you'd be comparing objects of two different kinds in your compare to. I've never seen it before, but it's possible you might see it. Anyways, so this is how we compare them. How does compare to work? Well, compare to will return a sort of score based on how O, which is the one we pass in as an argument, compares to this. Right? So the two things you're comparing in this are this, which is the one you're calling .compare2 on, and O, which is the one you pass as an argument. Now, positive and negatives are things that I often get messed up or mixed up on this, so we'll test it and we'll see if it works properly, and if it's not, we'll swap our positives and negatives. But generally, the practice is like this. We want to score for both, so we'll say int score of this is going to be equal to, say, let's say this plus this.pay multiplied by this.cool factor. Right? So we'll just multiply the cool factor by how much you get paid to tell how good this internship is. Then int score of other will be equal to other.pay times other.cool factor. Now you do want to make these the same, right? You don't want to be unfair, so you don't want to say that like 0.5 times that, because that wouldn't, or like 0 times that, because that will always favor this over the other one. You want the scoring system to be consistent for both. And that way you'll get a good comparison, and it'll sort the same order if you call this method in both ways. Then finally what we do is we return score of this minus score of other, and that should give us the final output. So what we can logically deduce from this what we can logically deduce from this is that if this internship is better, then it'll return positive, and if this internship is worse than the other internship, it'll return negative. Are there any questions about this whole compare to method and the comparable interface? Okay, I'm assuming then that you understand kind of how that runs. Now, there is another thing we might want to do in this. It's if we want to compare objects of different types. So if I have an object, let's say, of type summer classes, right? This one doesn't have pay, and it also doesn't have a cool factor. Maybe what we care about is like int num credits, right? The number of credits we do. We want to maximize how many credits we do. And then what we can do is we can actually set this up so we can compare it to an internship. Or if we want to compare, let's say, summer classes and internships, even though they're kind of different, what we could do is we can make some sort of base abstract class. So what we can say is we can say from our like tutorial 1 and 2, we can say class, let's say, summer activity is going to be an abstract class, public abstract class. Summer activity implements comparable summer activity. And now, if we make these ones both extend summer activity, extends summer activity, and then we need to implement our methods, and we're going to have to compare it to another summer activity. So instead of that, we'll change our method a little bit. We'll say that if the activity O instance of internship, then we can say internship, let's say intern, is equal to, cast it to internship, so internship O. And then we can say that, and then this will be intern. Right, and now if we want to compare it to a, what is the other one? To a summer class, we can say else. Let's say summer, or else if O instance of summer class, summer classes, we can say, oh, I forgot to extend it. So this one also extends summer activity, right? Implement method. We can say summer classes class is equal classes is equal to summer class, just cast it. Oh. And then we can say maybe score of this will be the same, and score of summer classes will be number of credits times 1000 maybe. Equals classes dot num credits, was it? Times 1000. Could make sense, right? I don't know if that's how we compare them in real life, but still, that's how we'll do it here. And now we'll just also return score of this minus score of other. And that way we can compare things of different types. So that's generally the way the comparable runs. With summer activity, we can just do the same thing. And here, and also if it's not an instance of either, we'll say they're the same. So now if we copy paste this code, we can do a very similar one inside of summer classes. We can say, if it's an instance of internship, then we will say that, well, actually, you'll have to do it slightly differently. So if it's an instance of summer classes, we can say score of this will be this dot that. Boom. This dot number of credits, right? And if it's an internship, we'll have to do score of this differently. So those are the general ways to do compare to. So what we did is we had a class called summer activity, which can be compared to other summer activities. So we're saying that we want to pick the best summer activity to apply to, right? Then we'll say that we want to compare our summer activities, sort them by highest score to lowest. Then we want to, well, apply to them with the highest score first, right? So we want to apply to our summer activities, but of course we don't have time to apply to every single one. So we have to sort them, and to sort them we have to implement comparable. And to implement comparable, when we extend summer activity, we have to override compare to. It's going to take as input a summer activity, and since we have these classes like this, we'll check what they're an instance of, and we'll set a scoring system based on what kind of object they are, right? So my scoring system is, if it's an internship, you multiply the pay by the cool factor to get how good the internship is, and if it's a summer class, you take the number of credits times 1000 to see how worthwhile it is to take. All right, so we have summer classes and we have internships, and we want to compare them, and we want to choose them based on which ones are the best. So what we can do is we can make a method. Let's call it, let's say public static void, or public int, or maybe public summer activity array to apply. And then here we'll take as input summer activity array of possible activities, and an int, which is the how many we can apply to, so max applications. And now the point of this method will be to, so start, we'll say this method will use sorting to pick the best summer activities for us to apply to of the possibly millions of possible activities. Now the reason we care about using merge sort here is what? Like, could somebody tell me what would be the reason why we'd use a fast sorting algorithm to write this kind of method? Again, our goal is to sort a massive array of summer activities, which is going to be of size n, let's say, and we want to pick the ones which have the highest usefulness, so the ones that we need to apply to the most urgently. To pick these, we're going to sort them, and then we're going to just return the first elements of the sorted array. Why would we use merge sort for this, and why would something like bubble sort maybe fail? Or maybe not fail, but take too long. Well, what's happening is that in this situation, I mean, you look out in the world, right? We have millions of possible activities we could perform. Oh, sorry, I saw the mic came on. Yeah, that's right. And imagine, let's say you have 20 minutes to decide which internships you're going to apply to and which summer classes you want to take. If you only have 20 minutes, and let's say there's 10 million of these options, a bubble sort will take way longer than 20 minutes to sort all of that. So your computer's not going to finish choosing for you in time. So for that reason, we have merge sort. And this is actually a very common real-life application. If you need to choose between a large number of options, a good algorithm for that is to sort the options using a fast algorithm like merge sort, and then to just take the first, here it's max applications, we can say like the first n of those items as our best choices. Those are the ones we should apply to. So to write this method, we're going to have to be able to compare anything. We can no longer do an int array, we have to do an array of something else. So what do you guys think? What should we put instead of the int inside the type of array here to make it compare anything possible? Like so that we can compare any possible type of object, what should we put in the int array here? Object could work, but remember, when we're comparing them, we're going to use the comparable interface. So this interface here, which implements comparable, which lets us call the .compare2 method. That's how we're going to compare our items. Because when we're sorting, right, we need to actually compare each item to each other item, right? So if we just do object, we have no real way to compare an object to an object. We don't know how those two things would stack up against each other. So is there something else we could put in the argument there instead of object, which would let us actually compare them to each other? Sorry, could you repeat? Okay, so the session today is about applications of fast sorting. And what we're doing right now is we're trying to say, we have the problem of picking out like what to do in the summer. We have millions of options, so internships, summer classes, whatever you want. We're calling them summer activities. And what we want to do is we want to sort all of the possible activities using merge sort and pick, let's say, the best 5 to apply to. Because, you know, writing the applications might take a few hours each, and you don't have so much time because you have so many classes. So you only have 5 possible things to apply to, and you need to choose the best ones. That's why we're sorting them. And here, score of this and score of other is actually for the comparable interface. Here in summer activity, we implemented the comparable interface. The comparable interface lets you compare this summer activity to a different summer activity. So if you have 2 activities, you can call .compare2, and then the summer activity you pass as an argument will be compared to this one, and it will return a number, and depending on whether that number is positive, negative, or 0, we can tell if this summer activity is better, it's worse, or it's equal to the one that we're comparing it to. Does that sort of answer the question, or was there something more specific you were wondering about? Yeah. Yes, you're right, exactly. So the way that we're doing this is kind of my way of explaining the comparable interface. It confuses a lot of people because compare to seems kind of abstract. Like you're taking an int, and how are you returning an int given some object? Well, what we're doing is we're basically deciding how profitable is this for us to do this option versus how profitable is it to do the other option. So here I've got two options. Either the other thing that we're comparing it to is an internship, or it's another summer class. If we're comparing two summer classes, we simply say that the score of this summer class, because we're in the class summer classes right now, right? So we either have the option of taking this summer class or whatever object is passed as an argument. So if the object passes as an argument as a summer class, we tell us, okay, so the number of credits for this summer class is this number of credits. The number of credits for the other one is class is that number of credits. We're going to multiply it by 1,000 so it can compare to an internship, because otherwise the internship will always win. And then we're going to say that let's say if the score of this is bigger, it's going to return a positive number, because if this is bigger than other, then it's going to be positive, and it's going to say that this summer class is better than the other one. If score of other is higher, it's going to say that the other summer class is better, so it's going to return a negative number. And that way we can use that to compare when we're sorting. When it's an internship, it's similar logic, except instead of saying score of other is the number of classes times the number of credits or whatever, we do here, it's the pay of the internship times its cool factor. So it's like how cool the internship is times how much you get paid, which is, I guess, how you would score an internship. And then, again, it's the same logic. You have this, the score of this will be the number of credits times 1,000. The score of the other one will be the pay times the cool factor, and then you'll see which one is better for you to take. So if the internship pays like $1 and is really lame, then obviously you'll take the summer class. And if the internship is really, really cool and pays a ton of money, you take the internship, right? So that's why the scoring system works the way it does, and that's kind of how the method works. Does that kind of make it more clear? And yeah, if the two options are equal, these two numbers will be equal and will return 0. So that way, it's a way that we can do a comparison. So it lets us sort things. And the reason that that method exists is because in our abstract class, we implement comparable. And this inside the triangle brackets is what kind of object we can compare to. So this inside the triangle brackets determines what the input of compare to is going to be. Okay, so hopefully, does that make it clear? Or was there something else you were wondering about it? Yeah. 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 Because here, what we're checking is what kind of an object is other. Because remember, we pass with summer activity, which is an abstract class. So we're deciding, is the activity an internship or is it summer classes? Because we can't compare a summer class and an internship in the same way. We have to consider them differently. So we're using instance of to see which one it is. If it's an internship, we compare it in this way, and if it's a summer class, we compare it in the other way. Okay, awesome. So now when we're going to sorting, right now our sorting algorithm, it takes as input an array of int. So what could we make our array of in order to make it comparable, like so we can sort any kind of comparable object? We could do summer activity, that would be valid, but I'm trying to make a really, really versatile merge sort, which is going to work on any kind of object at all. So is there something else we could use as the type? Well, there's a... Oh, sorry, go ahead. Yeah, okay, so it's because there's a little trick. In Java, we can actually use an interface as a type. So here it implements comparable. That means that this is an instance of comparable. So what we can actually do is we can say that we can take any array of objects that are comparable. And that way, we're going to know that anything in our array is comparable. And that way, we can also change this one to be comparable. Comparable. And now, we can compare the items in our array. Now, there's a few differences between how this works with, comparable versus int. The first one is that our internal arrays have to be comparable as well. And if you want details on how the merge sort system works, that is a good thing to look at tutorial from Tuesday. That's where we go over it in detail. Here, I'm just going to show what the differences are between comparable and int. So, first thing, we want to change all of our int arrays into comparable arrays. That's pretty self-explanatory, right? Because we just changed the array type from int to comparable. Now the next thing we need to do is the way we compare things. Here, we say if lower half index at lower half is greater than or equal to lower half index at upper half. For this, we use that method we wrote, the compare to method. We say lower half dot compare to upper half index at upper half. And now, to do the greater than or equal to, we simply take the greater than or equal to and we move it over. We say greater than or equal to 0. And now that's actually equivalent to what we had before. Compare to t a member of a raw type comparable. That's fine. We're just going to assume we have good inputs. If we want it to be very, very strict, we could say what kind of comparable. So we could say like comparable to summer activity, whatever, but we're not going to. We're just going to be nice to it, and we're going to assume that whoever's putting in arguments is going to only put things that are comparable to each other into the array. Don't worry about it. If you see exceptions, that would be why, but that's just, like, it's fine. We can just use the raw comparable. And now, if we try merge sorting, we can see that this no longer works with an int array. It needs to be comparable. But if we change this array from int to integer, because it's a wrapper class, which is comparable, now it's going to work. And if we run this mode, or this method, we should see that it's still sorted. It might be sorted in reverse order. If it is, oh, missing return statement. Where? Oh, I didn't do this one yet, so I'm just going to return null. Null, this one we haven't written yet. We're going to write this one afterwards, but first we want to show that this works. So we're going to run merge sort. And we can see that it's actually sorted backwards. So to fix the sorting backwards, we just need to make sure that we get our like less than or greater than symbol right. So here, instead of this order, we should probably move it like that. And now, if we run it, we should get it from smallest to largest. And we do. So our merge sort works, and now we can work on anything. So now we don't just have to store ints, we can actually store whatever we want. So instead of test being an array of integers, let's say we want to sort an array of characters, or strings. Let's say strings, because those are kind of more complex, right? So we can have a string AAA, right, BBB, whatever we want, BBB. Later we're going to sort the bmovie script, so that's going to be more strings, but for now we're just going to do this simple string array. BBB, and maybe I'll change these. BBB, this one will be CB, CV, blah, 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 blah. And these should be in alphabetical order afterwards, so ZZZ. And that should be enough to prove that it's going to be in alphabetical order, and this should be a string array. Boom. So now, if we run the method, instead of sorting integers, we can see that it's going to sort strings. And now our merge sort is going to be able to sort whatever kind of object. See, it put them in alphabetical order. So does it make sense, right? So since we changed it to comparable, now any object which is comparable, which includes all the Java objects, and any object we write that implements the comparable interface is going to output like this. Does it all make sense? Okay, awesome. So based on this, we can write the method to apply, which chooses which to apply to, like which of an array of possible activities we can apply to. So how do you think we'd go about doing this? Again, we need to pick... Oh, sorry, go ahead. Yeah, we could use a for loop, but we already have our sorting algorithm, right? So, and our goal is to pick the summer activities which have the highest score. So what could we do with it? Yeah. Yes. Exactly, that's completely correct. And this is something you'll see a lot of in Comp 251. It's called a greedy algorithm. The meaning of greedy is that it takes in like a large number of options, and it's going to just take the options which are the most profitable. It's like you're just greedy and you're taking whatever will give you the most money right away. You don't consider how they compare to each other or like any other possible criteria or what the consequences are going to be, right? You only take whatever is the highest score. So if you're playing a video game, that'll be, you're gonna just target like the whatever's gonna give you the most points, and you're gonna just do that. It doesn't matter what the consequences of that are. If you're gonna die afterwards or anything, you just do what's gonna give you the most points. That's what we're doing here, and it's a great algorithm for this kind of situation because it's gonna let us apply to the summer positions, the summer activities, which will give us the most benefit. So again, you're right. What we can do is we can say, to call our merge sort, we do divide. So we can say divide possible activities 0 possible activities dot length minus 1. I believe that's how we call divide, right? Yep. So that's going to sort our activities. So it sorts our activities from best to worst. Now all we have to do is we can just use a little loop to copy it. So we can say summer activity array output is equal to a new summer activity array of size max applications, and then we can say for int I equals 0, I is less than output dot length, and I is less than possible activities dot length. Now the reason I put this and here is that if the possible activities is smaller than our output, then we want to stop the loop. and then we say I++, and we can say output at I is equal to summer activities at I, or possible activities at I. So this is going to give us all the best activities in our output, and then we can say return output, right? So this algorithm should be pretty solid. We can try it out. So we can try it out on a small number of activities first, but that's kind of hard to do. So I'll actually bring out right now a quick technique that we use in making speed tests and other forms of testing, where we can generate random objects. So this is a bit of a deviation. What we're going to do here is we're going to create a public static summer activity array called random activities. And we're going to take an int size as our input. So it's going to generate random activities to fill up a certain size. Okay, so what we can do is we can say for each activity, or no, we can say summer activity array output is a new summer activity array, and inside it's going to be of size, and then we're going to fill it with random things. So we're going to say for int I equals 0, I is less than output dot length, I++, and we're going to say output at I is equal to, and now we can have a random number generator, so we can say rand is equal to new random, and here we're going to use that to decide what we put in. So first thing we want to decide is if it's a summer class or an internship. So if rand.next boolean, we'll do a summer or an internship, and if it's a integer, we'll do, or if it's else, it'll do a summer class. So here we'll say output I is equal to new internship with a no name, we don't care about the name, with a pay of rand.nextInt and a cool factor of rand.nextInt, and we'll say it's on a scale of 1 to 10, so the max value is 10. Right? Then otherwise, we're going to make our output a random summer class, so we'll say summer classes, and it's going to just be of credits that are between, and let's say 18. So I forgot to do a constructor for summer classes. Let's just do that. Okay, so now we can create this random array of a large number of summer activities. Now we'll return output, and we can see what's going to happen. When we call this method on a random array, and let's say we'll take size 10. Let's see what kind of applications we get, and let's see how those compare to our possible ones. So instead of doing all this, I'm going to say summer activity test is equal to random activities of size really huge. And then we'll say we're going to call summer activity array output is equal to, what's our algorithm called here? It's called to apply, and what we're going to do is, not to array, to apply. Is that not static? Oopsies. This should be static. Static of possible activities, and let's say we take the top 10. So we'll say to apply on possible activities or test with size 10, and now we can print out our two things. We'll print out test, and we'll system.outPrintln as well our output, and then we should be able to see that our test and our output are good. But before I do that, I should create a toString method. So we should say generate toString, and I want all the things. So I'm just going to create toString methods so that we can see code generate toString what is our various stuff. And then in merge sort, we're going to say this. Okay, so if we run this, we should see a really huge size 1 million thing. Actually, maybe I'll make it size 20 just to make it easy to see. And then we'll see the best ones in the second printout. So let's do that. We'll run merge sort. So now we can see that, let's also turn off our print lines. I put print lines into our array, or into our merge sort for debugging. Let's just turn those all off. Nope. Nope. Okay, now we should see it clearly. Start end. That's not right. Where is this printout? Give me 1 second. I'll get rid of all these print lines. Here we go. This one. Okay. Now, finally, after I got rid of all the useless print lines, we should see that our array first has all of these summer classes and other stuff that's kind of useless. So all these summer classes, like 0 credits, that's pretty bad. An internship with a cool factor of low should be bad. Like all these 0 credit summer classes, though, they're pretty bad. So let's see what our algorithm chose. It chose an internship that pays a really small number. And okay, so it actually is backwards. That's fine. So it looks like we did our compare to backwards. What we have to do, since it's backwards, is we have to return score of other minus score of this. And getting it backwards and forwards is just a matter of trial and error for me, usually. This one is like that, and then internship will also be like the same. So, okay, now if we run it, we should see our best ones at the start and our worst ones at the end. So at first, again, we've got like a pretty bad one here, 10 credits. That's not very good. So instead, it says the ones we should apply to is an internship that pays like 7.5 million and is really cool. Then an internship that pays a little bit less, but is still kind of cool. Then an internship that's even less cool. And then eventually, we're going to get down to our summer classes, which are going to take 12 credits, 10 credits, 9 credits. So we can see that it's going to order our things by how much we should apply to them, right? So first, we're going to apply to the internships which pay a ton of money. And then after we apply to internships that pay a ton of money, we're going to apply to our summer classes in order of credits. Does it make sense how this algorithm worked? How we're taking our most valuable things and we're doing them first. And the array we're outputting is kind of small. So if we just want to take the best thing, if we just want to apply to only the best position, we simply change our input from 10 to 1. And we're going to run it. And now we just get the coolest internship. Or if we take it, and we can make this of size whatever we want. And it should still always run reasonably fast because it's merge sort. And it should still output everything. So now it's taking a while. I think it's taking a while to print. Maybe I shouldn't have done something that huge. Okay, I'll try it with something smaller. Because I think that being that huge, it can't even print in time. Now doing it on a smaller array, we can see we've got this really huge amount of things we could possibly do. But very quickly, we got our best option. And our option may not be the best if my compare twos were out of order. So a little disclaimer, this order might be wrong still sometimes. So to really get this working right, we have to make sure that it always returns the one with the highest value. I think right now it thinks negative is good. So we should probably not generate internships that cost you money. To do that, we can just say in our generator here that our internships pay will be bounded by maybe, 100,000. Right now it's gonna probably give us a better representation. Anyways, all that aside, now we should get the best. Yeah, so our best option was internship, which pays almost 100,000 and has the highest possible cool factor. So that was the best of all of these. That's a greedy algorithm. Are there any questions about the greedy algorithm? Okay, great. So now we're gonna do something cool, and we're gonna sort the bMovieScript words alphabetically. So bMovieScript, as we know, is an extremely long script. It's a common thing to do to test something very long. So what I'm going to do is I'm going to create a string for the bMovieScript. So maybe static final string bMovieScript script is equal to, and now there we go. So that's our string. It's very, very long, as you can see. And what we're going to do is we're going to convert it into an array of characters, and then we're going to, or an array of smaller strings. We're going to basically split the string up by the spaces, and then we're going to sort it, and we're going to see in alphabetical order what words are in it. So we're going to change our main method here, or maybe I'll write another method for it. It'll be called bMovieAlphabetical, let's say. So we'll say public static string array alphabetical bMovie. And it's going to take no arguments, and it's going to put our bMovie into alphabetical order. So the first thing we do is we say string array all words is equal to bMovieScript dot split, and we're just going to split it based on the space. So if there's a space, we'll do that, and now we'll also say we'll split it on new lines as well. So all word is equal to bmoviescript dot split on new lines. So this is going to basically say every time there's a space or an enter, there is going to be, well, that. Actually, maybe instead of doing, no, it should be fine with spaces. You know what? I'm going to say spaces. It might be a little bit buggy with spaces only, but we'll live with it. Or maybe what I'll do is I'll say string script is equal to bmoviescript dot replace slash n with a space. So we're just going to get rid of the new lines, put spaces instead. Quick little fix. And now we're going to say we want to sort it. So what we can say is divide all word 0 all word dot length. This is going to sort it, and then we simply return all word. Now this is going to sort the bmoviescript alphabetically and give us the result. Very simple. Oh god, that's such a long thing. Anyways, where's my main method? Main. Now normally we'd read this from a file or something, but we haven't taught file IO, and I'm kind of lazy to write it now. So we're just going to do it like this. Too bad. So now we'll system.out.println arrays.toString of alphabetical bmovie. Now we'll run this, and after not too long, hopefully, we should get the result of all of the words from the bmovie in alphabetical order. And what happened here? Array index out of bounds. Did I forget a -1? Yeah, I did. Okay. Now we should get the bmovie script in alphabetical order. Okay, so it turns out U and comma are the last. We should probably remove commas. So we're going to start with dashes and symbols that are not... Okay, so the dashes come first because they are in the quotation marks and all the commas. Okay, we should probably remove commas from our string. But we start with, okay, then dots, and then we have all the A's. Atom, aborting, actually, okay, and then we go all. They say all a lot. Then and R, and berry. Okay, they say berry a fair bit. And bees, they say a lot as well. And then we can go through, and then we can see every word in the script has been now put into alphabetical order. Hello, hello, honey, humans, I. They say I. A very large amount. But now, what if we wanted to count the words? We don't just want to have all of the words printed out. Let's say we want to find how common each word is. Now, this is actually an application of hash maps, which comes later on in the course. But we can do it kind of inefficiently just with this. So, first couple steps I'm going to do before that, though, is I'm going to remove commas and all that. So I'm going to say, where's my method for the bmovie script here? We'll say script equals script dot replace comma with nothing, and then after the space, yeah, we'll sort them, and now we can loop through them. So we're going to say for string s in all word. So for every string in every word, let's have a what could we have? We could have a sort of a we should use a table for this, but we haven't learned them, so we'll use this an array list. We'll just import that, an array list of string. Nah, we really do need a map, don't we? How else could we count this? If the thing contains it, we can have a counter for each word. Yeah, we'd have to do an array list of pairs. So, you know what? No, I'm gonna do it properly. I'm gonna use a map. I know we haven't taught maps, but let's just say a map will let you. It's like a object-based array in Python, where you can use an object as an index. So for this, we're going to use the string as an index. We're going to say hash map. Don't worry, we'll learn these later on in the course. I'm just using it to demonstrate the concept here. Hash map of string, comma, integer, number of repetitions equals new hash map. That's just an import from Java. And now we can say if num repetitions dot contains key, so if it contains the string s, then what we'll do is we'll say, or actually first we'll say s equals s dot replace space with nothing, and s is equal to s dot to lowercase. So now we can probably do it. So now if it contains the key, then we're going to say number of repetitions dot put number of repetitions dot get our string dot or plus 1, and then we'll say s. Okay, so now we're going to increment our counter by 1 if the word is there. Else, if the word's never been there before, we can say 1. And now what we can do is we can just, instead of returning all word here, we can also print out, we can say system.println. Well, we actually have to sort them as well by the number of repetitions. So we'll say, well, we can do that. Or what we could do is we could just view it. So what's a good strategy for this now? One, we could sort it again using the integers, right? So we've sorted our array. We've put everything in. So instead of sorting it now, we can sort it afterwards. But instead of sorting it by the number of, instead of sorting it by the alphabetical order now, we can now sort it by the number of repetitions. So to sort it by the number of repetitions, we'll have to go through our map, and we're going to have to get a pair of our string and our number of repetitions. Now we could do this if we wrote our own hash map, or we can create a little class here, which is also comparable. So let's say class word is going to be like this, and then we're going to say string name integer num occurrences integer, and it's going to implement comparable as well. So implements comparable to another word, and then we're going to say implement methods compare to. Then of course we're going to say that return o.num occurrences minus num occurrences. Now we can sort words. So now we have to take everything out of our map, put it into words. So where is this method? Now we can say for hash map or number of repetitions dot entry set. So for entry string comma integer entry. This is just map syntax, so we don't need to actually learn this for COMP250. I'm just showing it as an example of the fact that we're sorting by the number of repetitions in the word. So map.entry of string of integer entry. In the number of repetitions, we'll say that words word array, and it's going to be the size of number of repetitions dot entry set dot size. And then we'll of course say words dot add. No, we'd have to say, yeah, we'd have to do an indexed for loop. So we'd have to say for map dot entry we'll have to say for, ooh, what's a good way to iterate through this? Oh yeah, okay, so int I equals 0, words at I equals entry, or a new word, entry dot get key, entry dot get value, all right, and then we can say I++, and then we'll divide word. And then that should give us the number of repetitions for each word in ascending order. So now we just have to create the constructor for word. String key integer value. Number of occurrences equals value. Name equals key. And now to know what word it is, we're just going to create a toString method. So generate toString. All right. Now we've got that, and now we should be able to just see our words in order. So now if we run our merge sort. Oh, did we have the wrong? Oh, yeah. I think I forgot to put the correct index here, so that's here. Words, words.length -1. There we go. So you have lots of words that occur only once, and then at the top of the printout, we should have words that occur very often. And do we split it up properly? We should probably also remove s dot equals s dot replace. S equals s dot replace. Dash with nothing. S dot replace. Period with nothing. Sorry, I'm just trying to get rid of all the periods and stuff so we can have a proper one. S equals s dot replace. Question mark with nothing. All right. And of course, s equals s dot replace. New line with nothing. Okay, now hopefully this should be more compelling. Jocks occurs once, okay, but if we go up to near the top, number of occurrences is 2. We can see that these words occur more and more frequently. And then right at the top, we've got our most common words. Our most common word is, okay, a blank space, or it's 2 apostrophes. No, it's just blank. Most common word is blank, and it occurs 1457 times. Then the word then you, then the, then I, which occurs 215 times. And we can see we sorted it by how frequent all the different words are. What we can do is we can also just say if we can keep improving this. We can, for example, say if dot s dot is blank, return or continue. Right. So there's lots of various ways we can optimize this. We can get rid of the blank, and we can get rid of the apostrophes, and then it can be more compelling. But we can see, for example, B occurs 56 times, R occurs 55 times. B without the 2 E's occurs 48 times. And then as we go down, all these words occur only once, like window and nice and bluffing and Manhattan. Those words occur once. These words occur more than once. I know hash maps you haven't seen before, but this is an application of how we can sort the words by how frequently they appear. Are there any questions about merge sort, sorting algorithms, these interfaces, or any of the things we've done today? Or is there any questions about, well, anything in general? The floor is open to your questions if you have any. All right, I'll give you like 1 or 2 more minutes to come up with any questions. If you're watching the recording and you have questions about this session, Piazza office hours are available, and you can also ask questions about this tutorial in the next one. Next tutorial, we'll be covering things like binary search trees, and we've got some cool animations prepared to help explain those. But if there are no further questions, then I'll be happy to move on, and we'll go on to the next topic. So if there are no further questions, then that shall be that. Alrighty, well, thank you guys so much for coming. If you come up with a question you weren't able to ask during the session, again, office hours and Piazza are open to you. Thank you very much, and bye-bye.